All right, thank you, Diego, also for the advertisement. Well, we resume today with Tong Li. We are very happy to have you here. It's a pleasure. She will speak about global Wellposedness and traveling waves of PDE models of Chemotaxis. Thank you.
Thank you very much for the introduction. And thank you, Diego, for the invitation. I enjoyed Brazil very, very much. And this conference is very well organized. I am impressed. So I myself listened to very interesting talks here. So here is the outline of my talk. And I may go through some of them quickly, some of them in detail. So this is the subject related with the math biology that I learned in recent years. So I will report the result that related to my work. It doesn't mean I exhaust the references. Okay, so I will talk about derivation of model and Wellposedness criterion, some initial boundary value problem, and special solution. Yesterday, someone talked about the traveling wave and stability. We are talking about nonlinear stability. And back to the original killer seagull model, the biological relevance, and some numerical result. So chemotaxis phenomena is a very common phenomena that happens everywhere. You have some chemicals, and you have some cell, and the cell may be attracted or repelled by some chemical. So you have two kinds. So one by the gradient of chemical. So if the chemical has some change, then you have some attraction. If there's no change, if gradient is 0, then there is no movement. So you can think of the chemical as food if you want, nutrition, or poison. If in the case of poison, it's not moving toward, it's moving away from the gradient of the chemical. So two basic kind. This mechanism is so common in biology, and it is everywhere, as you can see, finding food, avoid poison, development of wound healing. How comes your cut or wound can be healed? It's all because of this movement. It is because of this movement is inside immune system, cancer metastatics. In this chemotaxis phenomena, it was observed there are traveling band phenomena. This was the result of 1960. Adler. And they reported that they observed the traveling band. So there is the wave moving with constant speed and with the fixed shape. After this discovery, and Killer and Siegel developed a mathematical model, tried to model the traveling wave phenomena, traveling band phenomena in 1970s. And our model was derived from this 70 paper. This is another cartoon. It just say that why cancer is so hard to heal. And when the cancer was developed at first, it was slow and mild, but the mechanism is that the cancer cell invade the blood vessel. While it invade blood vessel, it grow. So there are two things going on. When it's invade and then grow. So that's why cancer is so hard to heal, especially when it's in the later stage. We are talking about a pretty late stage here. It's different from the case where the nutrition is being consumed, right? And this is not consumed, it's growing. Yeah, so it is very aggressive. It's very hard to heal. If you are at, if the cancer is at that stage, it's very hard. It invade and grow. And we can see through the differential equation. This was the 71 paper I mentioned. And of course, you see there are a lot of variations that will lead to different math model. So the first equation is about the cell, the evolution of cell density. U is the density. So it is, the rate of change is due to self-diffusion. And this term is chemotaxis. You see the gradient of C. C is chemical. So the gradient of C drives this movement of the cell and through this term. And the second equation is about chemical. The chemical itself can have diffusion. It can have kinetics, interaction between this and that. So in fact, this term can be different at a different situation. In a cancer cell case, this term is positive. So it invades and also grow. And in the nutrition case, this can be negative. So the interaction is negative, saying the food is being consumed. The nutrition is being consumed. But in other cases, this can grow. So these are some terminology in here. This phi is chemotaxic potential, and it describing the mechanism of signal detection. G is the kinetics. It is the interaction, and this kappa. It can be a function of U, but here it's a constant. It's the strength of chemical signal. And the important thing is that it can be positive or negative. So if it's positive, corresponding to attractive chemotaxis. If it's negative, corresponding to repulsive chemotaxis. Attractive is like in a cancer cell case. You will have a lot of accumulation and chances to get blow up. And repulsive is mild, is going away and away, and so you have more stable phenomena, such as stability of a traveling wave. So in this paper, in this talk, we most talk about repulsive chemotaxis. So we can describe the stability of it. For the attractive, we also we are doing some ongoing work. There are some other ongoing work I will talk about. In the history of studying this chemotaxis, there are major limiting cases. So, for example, in some cases, the chemical is already in equilibrium. So you have a zero here. So C sub T is not here. And then you have a parabolic elliptic coupling. And this system was studied by many mathematicians, famous mathematicians. And I did not list all of them because the reference is very long. And I only gave some paper and review paper that you can find a lot of references. And the topic studied focus on the existence, blow up, or the asymptotic behavior. The other limiting behavior Well, this is not that important that the chemical does not have diffusion. But anyway, if some chemical the diffusion is not very important for that chemical, you can use this to describe the movement. And that in this case, you have a parabolic and ODE, differential equation coupling. The work along these directions is less than the previous cases. So this is when I get involved. I learned this topic from my collaborator, Zhan Wang. He was a postdoctor at IMA at that time, 2008. So I learned a lot from him, and then I worked with some of my colleagues on this topic. In fact, we also studied the case of both diffusion rates are positive. They are different, of course. These two are different. And you can also study some of the phenomena such as the wave and Wellposedness and existence of wave and stability of wave. And we first studied the case with no vacuum. This is the density. So this is with the assumption that this is not a zero. At t equals 0 is not a 0. It will not be 0. And later we overcame the difficulty of this being 0 vacuum. This is by using the weighted energy estimate. So now I'm talking about my our model. So let's say we assume there is no diffusion of the second equation, the chemical. And this is the chemotaxis potential. It's a logarithm. This function was taken from the 1971 paper of Keeler-Siegel. It was this the form of logarithm that will produce a traveling wave. And also, there are experiments explain the singularity of c equals 0 of this function, log. So there are experiment support of this choice of function. In any case, this choice of function was taken from the original paper. And the kinetic function is minus alpha u times c. The alpha is positive, u times c. So this is a negative. So we are talking about the case where you have this one, yeah. This is negative. So this is a logarithm, log c. In this case, in this particular case, we can do a transformation, like a Hopf-Foucault transformation. If we make a transformation like this, and then we do some scaling, the original system becomes this. And we took the gradient of the second equation, so you get this. And this is different from before in that it is the nonlinear conservation law, and this is a conservation law system of conservation law with partial viscosity. And you have the quasi-linear term here. And this is also true for high D, higher dimension. And after this change of variable, then you do not see the singularity in the equation. At least on the surface, you don't see anything, log C or anything. It's just U times V and stuff. So it was through this transformation, we changed the original system to this way with the particular choice of the chemotactic function and kinetics. We can we focus now on the study of this, existence of a traveling wave and Wellposedness, the stability of this. This is about the Cauchy. So for that problem, you can study the Cauchy problem, and you can study the blow-up criterion, in which way a solution will blow up. This is the result we did. So the solution in initial data in this space, the lifespan is either a global solution, or if it blows up this way. And this V is the gradient of C. So the blow up is related with the gradient C. And that is the main mechanism of the chemotaxis gradient. It is attracted or repelled by the gradient of chemical. So this is the L2 estimate, how to get that blow-up criterion. We first did the integer index, and then we did the fractional index at subgroup space. And then at the end, you get this equation, so you can get that conclusion. The blow-up criterion is related with this. And we also proved that if the initial data is very close to a constant state, then there is a global solution, and the asymptotic behavior is that constant state. That's a small data, small near constant. With my colleagues, we studied the initial boundary value problem, 1D. In a 1D case, we can prove global existence for bounded domain. And the solution converges to equilibrium state. And the proof of this large data result is due to the entropy pair, the flux pair, the free energy, like and Bungari inequality energy estimate. Because this is like a Lyapunov function, global function, so you can do the large data stuff. It is this is the large data result. And similar result can be obtained for higher dimension, but the initial data must be small. We don't have the large data result for the higher dimension. And there are some previous result. And this previous result is also Fontella, Friedman, and Hubei. And they show the global existence for the 1D parabolic ODE model. That is without the change variable. And they also show that the solution converges to non-constant steady state. The non-constant steady state is very meaningful, biologically meaningful. It's called aggregation. So this was also very nice result, previous result. And we come back to the traveling wave problem because the singularity log C at C equals 0. So there was no, previously there was no systematic result on the existence and the stability of traveling wave. So we come back to the equation. This is the transformed equation. And now I have diffusion on both equations, diffusion. And they are not equal. This one is small. And this diffusion also enters the flux through that transformation. V equals the gradient C over C minus. And this viscous conservation law, quasi-linear, it has, if you don't look at this, look at the left-hand side, it is a genuine nonlinear hyperbolic system. So this is because we are talking about a repulsive case. If it's an attractive case, this will change type from parabolic to elliptic to hyperbolic. But now this is hyperbolic, the repulsive case. So we can study the special solution. One special solution is a traveling wave solution. That is, it is a solution of a special form. It has this function of a single variable, and S is the traveling wave speed. And then we have the left and the right state coming from the biology relevance. We have the sign. And this is a traveling fronts. So we have different left and right state, different. So it's not a pulse, it's a front. So the front represent, the front of a cell, and also front of nutrition. So the nutrition is being eaten, right? And the cell is moving toward the nutrition, the gradient of nutrition. So you have a front of a cell and a front of food nutrition. Okay, so that's the basic meaning, but it can be applied to more situations. So for the traveling wave, you see that's a 4 by that's a two second order ODE, because the equation is in conservative form, so you can integrate and you end up with two first order equation. And this is the conservation law, and that's the entropy condition, make the viscous profile exist, we call it that. And we pick the second characteristic family. And the two first order ODE, we can use the phase plane analysis. We can prove that the traveling wave exists, unique. Up to translation is unique, it's monotone. And the proof is a simple argument of invariant region. So here we have the Nauka line. This is another Nauka line. And it turns out, this is a saddle point. This is a stable node. And so the turns out you can calculate the flow direction. And it turns out the unstable manifold of the saddle, this slope is in between these two. So it goes inside. And then these two are isolated, stable, not stable. These two are isolated equilibrium point. So it can only go here. It cannot go actually round in here, because no equilibrium point, and also you cannot go around. This is the equation said it's monotone, because it's a prime, has a fixed sign. So this is a stable node, so it can only go there. And that is that's the traveling wave we obtained. And so such a traveling wave we obtained, we wanted to know whether or not the traveling wave is stable. The traveling front is stable in a sense that if we come back to Cauchy problem, the initial data of the Cauchy problem, if the initial data of the Cauchy problem is not very far away from the traveling wave, this is small, this is H1, this is L2. If this is small, this is antiderivative, I will introduce. If this is small, and then we can prove that the Cauchy problem has a unique solution, and the difference is in here. And as t goes to infinity, the difference is 0. And I did not write here, there. This is up to a translation. So you could have a translation in here, depending on your initial data. So that is the stability. So if you have a traveling wave, you have a small perturbation, and you prove that as t goes to infinity, it still goes to traveling wave maybe with a translation. So that is the problem we wanted to address. So the remark is, I already talked about that. The remark is that when we prove the stability of the traveling wave, we did not require this to be small. This is called the wave strength, so the front. And in physics or biology, this is not small, but with the restriction of the method, usually, I mean, the people in this business, you have to assume this to be arbitrarily small to begin with. In addition to say the perturbation is small, this is small, the left and right. But this is small is not required because of the system. So there's some technical detail proof. Because the equation, the system we consider are in conservation form, so we consider the antiderivative. If we consider antiderivative, we will gain one more regularity automatically. So this is the difference. That's the antiderivative. And we consider the initial data that the perturbation is along this direction. This is a special case. So that the Cauchy problem solution can be decomposed as this and that, right? This is just straightforward. And we just call this antiderivative. We're just going to work on the antiderivative because the conservation law, so you know that if this is 0 to begin with, and then this will be 0 at a later time. That's a conservation law. So for simplicity of notation, we will assume that is 0. If it's not 0, you can do a translation, you can carry it. So we could deal with the case that x0 is not 0. And after that, we go back to the system conservation law and do the integration, and then get the equation for the antiderivative. You integrate the equation for u and v. I mean this. You plug in the little u minus the capital U, then you integrate. You will get the equation for phi and psi, the antiderivative. So this is the antiderivative equation, nonlinear coupled, and we study them in this framework, the energy estimate. We are going to get the H2 estimate at the end. We are going to get the decay estimate, the boundedness and the decay estimate of the derivative. So the derivative is the difference. So the energy estimate result look like this. If you sum them up, this is H2, this is H2, and this is weighted L2. And if you can get this estimate, then you can get the desired result. This is the difference of little u and capital U. Yeah, this is Sobolev embedding. You can get what you want. The energy estimate overall look like this. This is with every term. We just put everything here, And also we keep track of the constant d and the constant epsilon, because they take care of different term, and this epsilon must be small. The most basic energy estimate is L2. So the L2 estimate is like this. You get the L2 estimate, and then you the other H1, H2 will be linearized, will be easier. So the hardest part is whether you can get the L2 estimate. The L2 estimate is you do the linear combination, not linear, combination of the first and the second equation, and then you get some energy estimate. In here, there is a key coefficient. This phi square, remember it's antiderivative. This is the lowest order term in terms of derivative. So if this does not have a sign, and nobody will come help, because this phi is the lowest order. There's a phi z, phi z z, phi z z z, right? This is phi. So, so the key step here is that whether or not this has a sign. And this is the derivative of the traveling wave. It's a function of z. We are in a moving coordinate z. And so we did the calculation, and it turns out that this one has a positive lower bound, so that this term is taken care of. You don't, if it's not, if it's negative, then you have to, you cannot go through this. So in the general system case, people assume the left state and the right state, they are close, U plus, U minus. It is because this term usually does not have a lower positive bound. But if you assume the left state and right state are very close, and this is very close to a constant, this will have a lower bound. But here, because of the system, the physical system does not require that. So we don't need to assume it is close to a constant. And that's the main difference. And of course, if you do this, they are all good, right? This term is positive, so this is bad. You still need to take care of that term. So you do energy estimate using other combination, and then plug into the previous inequality, and use the fact that this epsilon is small to take care of that. This is also lower order term. That's also, so you have to make use of the equation fully. And so that is the L2, and the H1 estimate is routine. You already did the derivative linearization, so all the difficult part is over, and the H2 estimate can be carried out. So you get the conclusion of traveling wave converge to, yeah. So you get the conclusion of traveling wave will converge to the initial value problem solution. If the initial data is a small perturbation, it will converge to the traveling wave. And we did go back to the original Killer-Segal model because we did change variable. And we wanted to see which traveling wave has a physical meaning and which has no physical meaning. And it turns out some of them, they are physical, and some of them not physical, because we did that change variable. So the traveling wave is about a nonlinear conservation law, the minus gradient C over C. And for example, you cannot assume that there are infinite many nutrition and stuff like that. They may be not physical, but some physical traveling wave and rigorous stability. Those are the new result. People did not do that before with the singularity. Some numerical, just say, so let's say here is the initial value, and we let the PDE evolve, and it will converge to traveling wave pretty fast. And this is another one. This is the initial data, and that is the later time. Later time, it becomes the traveling wave very fast. It's very stable. And from this, from this numerical, you can see that the initial perturbation may not be small. We know this is not small, but this is not small at all. It will converge to that very fast. So that is still an open question if you can prove the larger perturbation, because the method we used in this paper, we used in this talk, cannot deal with the larger perturbation. And you will have to need different tools, such as Lyapunov function, entropy-attribute pair method to prove that. But anyway, this is a pretty stable front. You can perturb it, and it will go there. Thank you for your attention.
Thank you. So